So first of all, I would like to show you guys what are we going to make in today's session. So is my screen visible? Sorry.
Yes, Utkarsh.
Yeah.
Yes, it's
Okay. Okay, great. So this is the project which we would be making in this workshop. Let me just enable the Odom frame. Yeah. So as you can see, it's an edge avoiding bot. It doesn't fall from the table, and we would learn to make it today in less than 2 hours time. So is it great? Are you excited, guys?
Yes, super excited.
so much excited.
Yes.
Yeah.
sir.
So then we can start with the project. So what I'll do is right now I have this workspace created. I'll just remove this workspace and I'll begin from scratch. So right now, if I want to see that if the workspace is there or not, so the workspace is not present. On tab, it is not getting auto completed. So I have removed the workspace and we will start making it from scratch. First, I'll make it from scratch. Then I have also created a GitHub repository for it. I'll provide you guys the link and you could clone and run it on your end. So yeah, we will begin. So first, what we will do is let me just clear the screen. Yeah. So first we will create a ROS2 workspace. In our case, we are going to name this workspace as bot, robot, bot, anything. So for that, you could just, for creating a directory or a folder, we use mkdir. We will name this workspace name as bot workspace. So I've created a bot workspace. I'm showing everything from scratch, like how to build the end project. So just follow along. And if you have any doubts, you can just unmute and ask. No issues. And also the recordings will be provided, so no worries. So the workspace is created. Now I'll navigate inside the workspace. There is nothing inside the workspace. Now I'll create a source folder, SRC folder inside the workspace. So we have a SRC folder inside the workspace. So these were the steps. Now what we'll do, we will create a package. This is the flow, like this is how we approach a problem in ROS. These are the steps we go through. These are the general guidelines which you need to follow. Okay, so we'll use this command to create the package. To create the package, you use this command, which is ROS2 pkg create. The package name we are giving it as bot description. So the description package contains the URDF of the bot and the Gazebo files and all those things. This is the general format which industries follow. So if you go by this, then your workspace will become scalable. Anyone in the world can see and understand your workspace. So bot description and the build type, the workspace type, we are building it as a CMake workspace instead of building it as a Python workspace. So our workspace has been built. But see, there was an issue. I built the workspace in SRC in the workspace folder only. I'll have to go to SRC first, and in SRC we will create the workspace. Our workspace has been created. Now we'll navigate inside the workspace. Don't have anything. We have, this is the general structure of CMake workspace. You can see include folder, SRC folder, package. So now once we have created the bot description workspace, we'll create few folders inside it. I'm not writing the commands from scratch or else it will take a lot of time. So we are creating 1, 2, 3, 4, 5 folders inside it. One is the launch folder, one is the models folder, one is the RViz, URDF and worlds. So the launch folder will contain the launch files. I'll later explain what are launch files. Models folder and worlds folder are related to Gazebo and they store the Gazebo worlds and models. RViz is the ROS visualization tool. So in the RViz folder, we will have the configuration file of RViz. And in the URDF folder, URDF stands for Universal Robot Description Format. like the computer doesn't understand the structure of your robot. You have to convert the structure of a robot in a code form, XML form, that it understands. So the structure of your robot will be present inside the URDF folder. So we'll create these folders. These folders have been created. Now what we'll do is we will go back to bot workspace. Now we will open VS Code. I hope that VS Code is installed in the PC of you guys, but still. So to open VS Code, you just navigate to the folder where you want to create the root folder and type code.space. Okay. So now we are in VS Code. I'll just increase the size a little bit. Okay. So is this visible, the VS Code part of it?
Yes, Utkarsh.
Yeah. So we have created all these folders. Now we have opened VS Code. Now in the URDF folder, we will create one file name as bot.base.xacro. Okay. So we have created this. In the xacro file, what we will do, I'll just paste the code and I'll explain you guys. Let me resize this. Yeah. So this is the basic structure from where we start using when we are coding in URDF. So inside this, we'll write the entire code. So these are the tags included. Then first we'll create a base footprint link. So I'll explain you later, like why we create a base footprint link, but this is the general, I'm going by the general guidelines as to like what the industry follows. So first we'll create a base footprint link. Then what we will do is I'll explain you this. What is this?
Hello, Utkarsh.
Yeah.
Sorry to interrupt. Can you please share the GitHub repository with us, like that link?
Okay, sure. Let me share it now only. It would be better, like you guys can go along.
Thank you.
So should I share? I'll share in the chat box. So I've created this repository. I'm sharing this thing with you guys in the chat box. So you guys can copy the repository, and these like this, the README file contains all the steps as to how to install ROS and how to source ROS and how to install Git and like how to install all the dependencies using ROS-dep and all these things. However, once we complete this project, at the end, I will discuss the entire GitHub repository, how to download and set up on your system. Just be with me. So I've shared the link. Yeah. So what we did here was first we created a base footprint. Then we want to create the main chassis of the robot. So that chassis, the red box which you had seen, so that we name as base link. Okay. Then we have to provide the visual tag. Visual tag contains a few things. So here, this is the geometry, the robot size which I want. So I have given a box of size 0.7 meters, 0.5. This is length, width, and height. All of these things are in meter. You have to give it like that. In material, you have to provide the color. So I've given red. This is RGB. So R is 1, G and B are 0. So the bot is of red color. And this is transparency, as to you want to make your bot look solid or translucent and so on. So this was the basic tag. These tags are used when you are simulating your bot in Gazebo. This is the inertial tag. Like what is the inertia of your bot? What is the mass value of your bot? And all those things. These are all those things. And this is again required when you are simulating in your bot in RViz, the collision tag. So collision in Gazebo tells the physics engine that the wheels are this stiff and this is this kind of object, and accordingly the physics engine behaves. So for that we provide the collision for the bot. So yeah, so this is the link. Then one more thing we have to provide is You have to provide the joints or else the bot won't get spawned. Okay. I've shared on WhatsApp the GitHub repo, and it also contains the README. From there, you guys can download. Okay, so we have inserted the link. This is the base link, the red box which you were seeing. And
Hello.
this is the joint. Yeah.
Can you please tell me what is XACRO? Because I'm the beginner, so I just
See,
want.
yeah, I'll tell you what is XACRO. So I told you what is URDF, Universal Robot Description Format. So generally people create their bots in the URDF format, like you'll name it bot base.urdf. But I generally prefer to create using XACRO, which you will get to know a little later, but I'm telling you now that XACRO provides you modularity. Like if you have a very complex bot with a huge number of links and joints, then one file only will have around 2000 to 5000 line of codes. And later it would be very difficult to debug. So what XACRO does is, using XACRO, you can break your bot into segments. Like one segment contains the URDF of the base, one segment contains the URDF of the arms, and it becomes easier for you to debug. One reason is that XACRO provides modularity. Second, what advantage you get using XACRO is you can create functions in URDF. Now, what what is the reason for creating functions? If we want to do a repetitive task, like in a code, if we want to do a repetitive task, we don't write the logic again and again. Instead, we create a function for it, and we send the parameters, and the function, one segment of code only gives the output to us. So in XACRO, you can create functions, like if you want to define multiple links, and the entire chunk of code is same, just the values are changing. So you have created a function with variables, and you are calling that function and only changing the variables, and the output remains same. So these were the two main reasons using XACRO. Yeah. So till here we are done. We have created the URDF of the red box, which was the base link, the chassis of the bot to which the wheels were attached. So now what we will do is we'll try to visualize this in RViz. So for that, I'll create a main URDF file wherein I'll include the XACROs. So your question will be answered now. So what I'll do is I'll name it as bot.urdf.xacro. This is the main XACRO file which would be published to the robot state publisher, with which ROS would know the joints and links, what all things are there in your bot. So again, for creating this, we'll have to paste this tag. From here we start, and yeah. So again, this is the general tag which I showed you earlier. And here I'm including the XACRO file which I created, this bot-base.xacro. I'm including in the main XACRO file. So this is folder name is bot description. From URDF, we are importing bot-base.xacro. So this I have included. Now what we will do is we'll create a launch file to launch these things. So see, you can launch RViz directly from command line using RViz2. If you write on the command line, RViz will get launched. Like, let me show you. If I'll write here RViz2, it will launch RViz. But RViz doesn't know from where to take your URDF and which topics are you publishing to, which topic you want to subscribe to. RViz doesn't know. You'll have to write few more commands on the command line for RViz to know, like where is the URDF published. It gets published to robot state publisher. So to avoid those steps, since we have a very limited amount of time, I have already written a launch file for you guys. What a launch file does is, like if you want to run 4 or 5 nodes, what are nodes? Nodes are specific chunk of code which perform a specific task. Like you can write a node for camera, it only captures images and sends to image topic. You can write a node for motors, it subscribes the command velocity and commands the motors. So these are nodes which perform a specific task, and the node communicate with each other in ROS via something known as topics. So one node publishes to a topic and the other node subscribes from that same topic. And this is how things work. So when you want to run multiple nodes at the same time, instead of running every node manually, you create something known as a launch file. Launch file, you provide all the nodes or other launch files, and you run a single command and it runs everything for you at the same time. So it removes the manual labor. So what I'll do is I'll create a display.launch.py. Okay, again, this is the general trend. If you want to launch RViz in industries, you always name it as display.launch.py. This is the general guideline. So I'll copy the launch file here and I'll paste it. So again, this is the launch file. I can explain a few things to you. Most of you might understand or may not understand, but I'll try to explain. So this is the robot description parameter where we are passing the XACRO file, the URDF file which we have created. And we are running the robot state publisher node, which subscribes from this topic and publishes it. We are running the joint state publisher, which creates fake encoder values. So I don't think like for beginners, it would be difficult to understand, but RViz is constantly subscribing from somewhere and then it is publishing and displaying you the results. So right now, since we are not working on real robot, or since we have not launched Gazebo yet, so the bot will not get any real values like from the encoders. So for that we create fake nodes or the encoder fake encoders. So this is the joint state publisher, what it does. And here we are launching the RViz node. So I'll just launch it. Before launching, you have to configure a few things as well. So here I'll paste the RViz configuration file. So it is nothing like what settings you select in RViz, it gets saved. So to save time, I'm directly pasting the configuration file of RViz. So we have the launch file, we have RViz configuration file, we have URDF. Now we have to set up cmake_list.txt. Again, it tells ROS that these are the entry points, these are the folders present, and from where all we'll have to access the workspace, the packages. So this is what cmake_list does. So in cmake_list, it is the entire same format, just I have pasted these things. So we are installing the directory, and in that we are adding what all folders we have included here. We have included launch, models, RViz, SRC, URDF, worlds. All these things are added here. If you'll not add this, then ROS will not recognize the folder which you have created. So in the CMake list, you will have to add this. And in the package.xml, we tell ROS at the time of execution what all packages it needs to depend on. So right now, exec depend, that is depend during the execution, what all packages it needs to depend during runtime. So these are the packages which it needs to depend on. So we have created this thing. We have set up CMake list package. We have created the URDF. Now what we will do is we will build the workspace. So to build the workspace, so as to make ROS know that something known as bot description exists on the system, we'll have to build the workspace. So what we will do is we will navigate inside the bot workspace folder, which we are in already, and we will do colcon build. We press enter, the workspace should get built. So it built the workspace. Now to run the RViz, we'll have to source it once again. So every time you want to run a launch file or a node, you have to source your workspace. So to source your workspace, this is the command. You go inside your workspace and you do source install setup.bash. Press enter. Now what we will do, we will run the display RViz. So for running RViz, we have command ROS2 launch from which package we want to launch. So we want to launch from bot description package. So ROS2 launch from bot description package. Which launch file do we want to launch? We want to launch the display.launch.py. We press enter. Okay. Here we are able to see the bot. Can you guys see it?
Yes,
Can
Utkarsh.
someone? Yeah.
Yes, sir.
Yeah. So here is the bot, and we have defined two links. We have defined base footprint and a base link. So if you'll go in the, if I'll disable the robot model, then you can see two links here. So this link is the base footprint. Maybe we can name it as well, I guess. Show names. Yeah. So here you can see that this is the base footprint. And since we want the chassis of our bot a little elevated from the ground, so we have created a base footprint which stays in contact of a ground. And then we have created a base link, which is a child of the base footprint link, and it is elevated. So this is the main reason why we create base footprint in cases. So yeah, so this thing is working. So you got to know two things, like you have to use XACRO to debug your code easily, and every time you have to build your code using callcon build, or you do symlink install, or else your code won't work even after making changes. Yeah. So now we will quickly move ahead. So our workspace is built, everything is launching. Now we will add the wheels to it. Okay. Second. Yeah.
Can you please say
So-
again, why did you say footprint?
Sorry.
Why did you create the footprint?
Yeah. So as I showed you, once again, I'll open and show. So this is the base footprint, and we want our chassis to be little elevated, because if the chassis is touching the ground, how will the bot move? So we create a base footprint, a base footprint link, and we create another link named as base link, and we refer the base link. We take reference from the base footprint and we elevate the base link. Like base link is the parent of base footprint. So in short, if we want to elevate a chassis, or if we want to create a base link not in the center but rather in the front of the robot, so we have to take a reference. So that reference is the base footprint. Did you get it?
Yeah, I got it.
In short, it's a reference link, or else how will you, like, in reference to what would you define the base link? So just to take a reference, we define a base footprint. It's not a real link. It's just a reference kind of a thing. Okay, so now we will add the wheels. So here I have added the right wheel. Again, the link name is right wheel link. These are the inertial tags relevant only for Gazebo. Again, collision tags relevant only for Gazebo. And this is the visual tag. In this, to create a wheel, I'm using a cylinder. I'm giving the cylinder a radius of 0.15 meter and the length of, that is the thickness of the wheel, it is 0.05 meters. Okay, and the material to create the wheel, I'm using blue. So R, G, and B. So B is 1, so it is blue. And again, you'll have to join the wheel to the base link. So this is the right wheel joint. So the wheel, so as you have seen that here, the joint was fixed, like the base link is fixed to the base footprint. So we don't want them to move, but I want the wheel to move, to rotate with respect to the base link. So here the joint type is continuous, depicts continuous motion. Parent link is base link. The chassis, the red chassis is the base link, and the child link is the wheel link. So the right wheel is attached to the base link, and the base link was attached to the base footprint, the reference link. Okay, so here I've added the right wheel. I'll quickly add left wheel as well. Everything will be same, just the coordinates would change. So here it is 0.275 and here it will be minus 0.275, just to see right and left. And all these things, for your information, when building your own robot, you'll have to do it, like you have to do it in a hit and trial, where you put some values, you open RViz, you see if the values are right. If not, then again you change. So before this workshop, I have done hit and trial, and finally I have come to these values. So to save time, so now since we have included the right and left wheels, and Since we did Symlink install, now we don't have to build the workspace once again. We can directly launch this thing and it should come. So here you can see our wheels have also come, and the wheels are touching the ground, but the chassis is little above. So that's why the base footprint. We don't want the chassis to touch the ground. And this is the robot state publisher. It provides fake encoder readings to the wheel. RViz subscribes from it, and based on that, RViz moves the wheel. So as you can see, the right joint, right wheel is moving, left joint, left wheel is moving. Okay. So
Kumar, can we
yeah.
create another XACRO file separately for the left and right wheel and include
Yeah,
that to the main?
definitely you can do. It's up to you. But I would suggest that you should, like, for a general guideline, you should create a XACRO file for base link. Sorry, the base, there should be one XACRO file. It should consist of the wheels and all the things which are there in your base. For sensors, there might be another XACRO file if you are using multiple sensors. If you are using arms on top of your robot, then you can create different XACRO files, which we will look further. So the wheels have been added. Now there are two wheels, but the bot will wobble as there is no support. So we'll add two caster wheels, one at the front and one at the back. So now I'll add the caster wheels to it. So again, the caster wheels are not movable. They are fixed wheels. They just slip on the floor. So this is the front caster wheel, which we have added. I have kept this as sphere. So also one more thing I'd like to share with you guys. Whenever you are simulating a bot in Gazebo and you are using a cylinder here, try to use a sphere in the collision. In this code, which I have uploaded on GitHub, it's not there, but in my original workspace, I had used a sphere. What it will do, and it will save you a lot of time. A cylinder in Gazebo has multiple point of contacts on the field, on the ground. But when you use a sphere, it only has a single point of contact in case of Gazebo. So it would reduce friction and your bot will move very smoothly if you are facing an issue. If you are not facing an issue, then it's not a problem. Initially, when I was a beginner, I used to face an issue like this issue I used to face a lot. So yeah, this is how you define a sphere for single point of contact. The front caster wheel we have added. Now we will add the rear caster wheel. So again, just the values will change, the coordinate values, everything is same. So here we have added the caster wheels. Once again, we will see if our caster wheels are appearing. So here you can see that our caster wheels are appearing. I'll disable the robot model. So this is the basic structure of our robot. I'll enable the names, frame names. Show names, yeah. So it's not that. So this is the base footprint, base link, right wheel, left wheel, front caster, back caster. In total, we have, these are called transforms. So again, the transform is a very big topic to cover. Transforms and homogeneous transformation matrices and all those things which happen at the backend. But in general, these are called transforms, TFs. These are called TFs, transforms. Or you can also call them joints. Okay. And the thing we defined, the robot model, these things are called links. Okay. And these are the joints. So our caster wheel is added. So the chassis of our bot is ready. Now we'll quickly add a edge avoiding sensor to our bot. So for that, I'll create one more XACRO file. I'll name it as bot sensors.xacro. Okay. Now what I will do is I'll paste this. So this is the laser link which we have created for the Lidar. So for detecting the edge in this project, we are using a Lidar in a very clever way, which I will show you as we proceed. So generally the Lidar is horizontal, but in our case, we have made the Lidar vertical and look forward, and it's detecting edges like that. So I'll show you how to do that as well. So yeah, so laser link And again, you can provide any geometry you want, box or anything. And joint, it is a fixed joint since it is not required to move. It is joined to the base link and the child link's name is laser link. Okay. So I'll save. Now since I have included a new XACRO file, I'll have to copy this XACRO file in the main URDF file, bot.urdf.xacro. So I'll just paste it here. So again, I have included the bot sensors.xacro in the main file. Now, since we have added a new file, sensors, again, we'll have to build the workspace. So call con build symlink install. And since we have built the workspace, again, we'll have to source the workspace. Then we will launch. So now you can see that one more sensor, the Lidar sensor is present at the front. And this is the transform of it. Okay. So our bot's URDF is ready. So we have reached till here. So do you guys have any doubts till here? You'll give the bot box size as 0.7. You'll see that the box is too big. Then you'll reduce the size to 0.5. Again, you'll launch RViz. You'll see that now it's fine. So you'll keep that. Then you'll move on to changing other parameters. And similarly for wheel positions, you'll see that the wheel is very far from the base link. So you'll not want that. So you'll again do hit and trial. It will come somewhere here. Then it will come here. So it's by hit and trial. Rest, the structure is the same. This is the general structure which you don't need to understand anything in it. It's the general structure that you follow. So yeah, that's the way to go. So
Okay, thank you.
yeah, welcome. So now since we have built the URDF of the bot and all these things, I had provided you what XACRO does. So we are able to now make the bot. Now we will try to simulate this bot in Gazebo. So for that, we will create a XACRO file for Gazebo. Gazebo.xacro. Okay. We create a XACRO file. Again, you start a XACRO file always like this. The basic structure. There is nothing to understand in this. It's just a basic format which you need to know. This is the bot name. You can give it anything. You can name it my bot or humanoid or whatever you want to name your bot. No worries. It's not that the bot name should be same as the workspace name. It's not that. However, a general trend is that your workspace name should start with your bot's name and then underscore WS workspace. Okay, so now we will add in this, we will add the Gazebo links, Gazebo tags. So here we have added the Gazebo tag in which we are referencing the right wheel link. These are the friction coefficients. These are the friction values. You can read it here as well. Yeah, so these are the friction values. I have kept friction very high so that the wheels, the left and right wheels do not slip and they get maximum contact and grip. Again, Kp is the dampening coefficient, spring stiffness, like we want the wheels hard and stiff. So again, we have given it a large value. Kd is dampening and minimum depth, maximum velocity. Again, this is FDIR. So this is friction direction. We want the friction in x-axis. So it will push the ground backwards and all those physics. So yeah, so this is friction direction. So right now it is given in the x direction. You always give in that direction only unless you are using some other kind of wheels like swivel drive and all those things. Right now we are working on a differential drive. So this was it. And now we will paste the left wheel as well. It is same as right wheel. I'll paste for the caster wheels. So caster wheels, the friction coefficient is very minimal because as I told, the caster wheel will not move. It requires to slip on the ground. So the friction coefficient is very less so that it slips. You cannot give 0 because at the end of the day, Gazebo is a physics engine. It will not accept 0 value. So yeah, back caster and front caster. Now we will add the sensors plugin so that Gazebo can simulate our sensors. So this is the plugin which you will use in ROS2 Humble. I guess it will not work if you are using Jazzy and the one which is the Gazebo which is compatible with Jazzy. I'm not sure, but it will definitely not work with classic Gazebo. In there, you have to change the type to, I guess, laser or Lidar something, which you can easily find on internet. But this is for ROS2 Humble Gazebo Ignition. So sensor name is Lidar, type is GPU Lidar. I'll explain this point later. Why is this 1.57? Like I told you, if you keep this, okay, I'll come to this later. I'll come to this entire section later once we simulate the bot. Let me just, for now, let me just change the samples to 360. I'll explain what samples are, and let me just keep this 0.0 only. Okay. So this is X, Y, Z, roll, pitch, yaw, RPY. I'll come to this later. I'll explain. So since we have added Gazebo XACRO file, we have to add this in the main URDF file. So we have added the Gazebo XACRO file as well. Now to launch Gazebo, again, like there was a launch file for RViz, there is a launch file for Gazebo as well. Either you can launch the Gazebo servers manually using command line, or you can have a launch file which does everything for you. So we will name it as gazebo.launch.py. We'll paste the launch file here. So again, to this, the robot state publisher is publishing and it is subscribing from the URDF. And here the Gazebo servers and paths are all getting exported and launched. Robot state publisher. Here the main Gazebo launch argument, it's launching Gazebo. So if you launch Gazebo using command line, you'll have to write this in command line. So instead of that, you just get package directory and you are launching this main launch file, which is integrated in the Gazebo package itself, which is like you'll have to enable that option wherein you can see hidden files. So this is what we use to spawn the bot. So we are using this to spawn our bot in Gazebo, the bot which we have created. And right now we are spawning, let's spawn our bot at XYZ0 and RPY0. Later we will spawn it at 2.0. I'll also tell why 2.0. Again, if you use classic Gazebo, so Gazebo used to access directly from the ROS topics, but the newer versions of Gazebo have their own topics. So you need a bridge which bridges the topics of Gazebo to ROS topics. So this is ROS GZ bridge. So here we are bridging the clock. Gazebo has its own clock, RViz has its own clock. To synchronize them, we are using a bridge, and we are using the scan sensor, laser scan sensor, the Lidar sensor, the plugin to bridge. So this was a quick description of the Gazebo launch file. Now we will build the workspace, and before that, we'll have to create a world as well, because where will Gazebo launch? So we'll create an empty world. 1 second. So we have created an empty world, and in this empty world, I'll paste it. Again, this thing you don't need to know. It's the converted into code. So this is the empty world which got created. And in the launch file, we'll see that Gazebo is launching the empty world only. So yeah. So in the launch file, we have created an argument wherein Gazebo asks which world, the launch file asks which world do you want to launch. So right now I have created an empty.world. So I want to launch the empty world only. And here it is adding the prefix .world. And this command will be sent to the command line. So the launch file does that on behalf of you. Okay, so now we have created that. I guess now we should be able to. Yeah, now we should be able to build the workspace and launch it. Again, we will do Qualcomm build symlink install. We will source, and this time instead of launching RViz, we will try to launch gazebo.launch.py. Let's see if it works. So as you can see that our bot is getting spawned successfully in Gazebo. Can you guys see the screen?
Yes, yes, it's visible.
Yeah. So our bot has been spawned in Gazebo, and now I'll enable the Lidar sensor as well, like to visualize it. What we will do to see the available topics, we will do ROS2 topic list. So yeah, so as you can see that the Lidar topic is available. So the Lidar data is published to scan topic. And you can see the robot description topic. To this topic, the URDF is getting published. And this is the clock topic. This is the joint states, which constantly tells RViz and Gazebo as to where the wheel position is right now. And these are the TF topics, which one, this receives the dynamic transforms, which are changing in real time. And this receives the static transform. Static transform is what? Base link to base footprint. This is static. This doesn't change even if the bot moves. Base link to sensor, this is static. This doesn't change even if the bot moves. However, base link to wheel, this is dynamic transform. Every time its orientation is changing with respect to the base link. So this was the difference. So for now, our bot is getting successfully spawned in Gazebo, and the world has been created. Now what I will do is right now we are launching the bot in an empty world. Now I'll launch the bot in a world with tables. So our bot will be present on the table. So for that, I'll create another file named as empty underscore table dot world. So how you have to do it, like if you want to create your own files, there is something known as Gazebo models. You'll have to add the Gazebo models in it. I have already added. I'll copy from here. I try to paste it here. It doesn't get pasted here. I'll go to the main file. Second. So I'm pasting in the bot description in the models folder. I'm pasting the table model. Okay, so on the internet, you'll get different models, whichever model you need. So you can download that model from there, paste it in the models folder, and then you can edit it in the Gazebo, and then you can save the code on your system for that world. You'll have to save it in .sdf format. Then later on, you'll have to convert it into .world format. So here I have created the empty table.world. Now instead of spawning the bot in an empty world, we will spawn the bot in empty table world. Okay. So now it will pick up the empty table file. Since we have added new files, we'll have to build the workspace again. So we'll do this. And again, we have to source. If some of you are seeing CBS, so what is CBS? CBS is Qualcomm build symlink install. I've created an LIS for it, a shortcut for it, so that every time I need not write Qualcomm build symlink install, I just write CBS. It runs that command at the backend. So now
You can show us how you created that.
yeah. So for that, what you do, you open your bash rc file using gedit gedit.bash rc. You open this. This is the bash rc file, and I'll just try to the font size is not getting increased, but anyways, so this is how you create. You have to use the keyword alias and what name, variable name CBS, and in that you have to paste the command Qualcomm build symlink install. Again, for Qualcomm build, I have pasted this, and to source the entire workspace or the entire ROS, I use SC. So source.bash rc. So this is the thing. You just have to write this much in your bash rc and it will work. So Again, going back.
Got it. Thank you so much.
Yeah. Sourcing it and launching Gazebo. Okay, so now you can see the table is getting launched, but our bot will be somewhere under the table. So that's why we have to elevate the bot in Z axis. So what we will do is we will again navigate back to the launch file, and while spawning the bot, where we are spawning the bot, here we are spawning the bot, we will keep it as 2.0. Like I want the bot when it is getting spawned, spawn it 2 meters above the ground. So now when we open, the bot should be above the table. Since we haven't added any new files, we don't need to build the workspace again. We can just launch. So we had done symlink install. So now you can see that the bot is above the table. Bot is getting spawned above the table. Now the bot is ready, URDF is ready, world is ready, but you won't be able to move the bot. Now to move the bot, you'll have to add ROS2 control to it. Now we will quickly move towards that. So to add ROS2 control, first you'll have to add ROS2 control to the Gazebo, this thing only, gazebo.xacro. With that, I have also added the ROS2 control plugin for making the bot move. And this is taking the bot controllers.yaml file to get all the parameters. So we'll quickly create a bot controller package wherein we will create a YAML file for the bot parameters and all those things. Before that, we will create a ROS2 control.xacro. We'll create a ROS2 control.xacro, and in it, we will paste this. So this is basically the ROS2 control part of it, wherein you define the hardware plugin, and it is simulation or hardware, and you define the joint states, right wheel joint. This is the command interface. So command interface is what this comes under this topic known as not hardware interface exactly, but system interface. Yeah, it comes under that topic. So it has two things: command interface and state interface. Command interface is what commands we give to the bot. So we are giving bot only velocity commands. State interface is what commands bot gives back to us. So bot gives back to us the position command and the velocity value, what it reads from the encoders. So this is the input part which we give, and this is the readings which we get back, and it forms a closed loop system. So this is the state, like what is the current state of the motors, position and velocity. This is the command. This is the parameter 4.5. This is the radians per second in which the wheels can rotate, maximum velocity in radians per second. So this is the ROS2 control part of it. Now to run ROS2 control, we will need to add the controllers package. So for that, first we have added a new XACRO file, so we will paste it in the main URDF file. So here I will paste the ROS2 control.xacro and save it. Okay, this thing is done. And then we will create the controllers package. So to create the controllers package, again, we will go to SRC source folder. Here till now we have the description package which contains entire Gazebo and RViz and URDF things, all those things related to that. Now anything related to motion and control we do in the controllers package. So again we will use this command only, ROS2 package create. Package name we want to give as bot controller. Build type, again we want this package to be a CMake package. Okay, we'll press enter. Now this package has been created. So we have two packages, bot description, bot controller. Again, we will go to bot controllers package. Again, the file structure will be same, CMake include package SRC. We'll need to add two files in it, which are this. We'll need to add a config file and a launch file. Config file will contain the bot controllers.yaml file. Launch file will launch the controllers. So we are done with this. we will navigate to the controllers package. In the config, we will create a new file, bot controllers.yaml. It's a YAML file, YAML, whatever you call it. Okay, in that you will paste this. Again, this is a template kind of a thing for all the differential drive robots. It remains nearly the same. So here you are including the differential drive plugin. This is the joint state broadcaster plugin. Update rate is 100 Hertz. This is relevant when you are communicating your ROS with your hardware. Then it plays a very important role because there are a few microcontrollers which cannot work at this rate. So then you have to tweak these parameters. Then again in the wheel controller section, we are defining the left wheel joint and the right wheel joint. We are not using stamped velocity. We are using plain unstamped velocity. So the command velocity you publish, which we will look very soon. So the command velocity is of two types. It uses two types basically to publish. It uses twist and it uses twist stamped. The twist is a message type. It contains, you can see the message type ROS2 interface show, and then you could paste the twist command. So it will show that what all things are inside the twist message. So here we are using twist message instead of using twist stamped. Twist stamped contains timestamp as well along with the twist message. Publish rate is 100. Wheel separation is 0.55. How do we calculate this? Our wheel was at 0.275 meters away from the base link. So into 2, you get the wheel separation. Let me show you. Okay. URDF. So if you see, the right wheel is 0.275 meter away from base link. So 0.25 this side and 0.25 at the other side. So the separation between wheels is 0.275 into 2, which is 0.55. Again, wheel radius you'll have to give. So in our case, we have given the wheel radius as 0.15. These things, wheel multipliers and all those things are there. Base ID you'll have to give. Command velocity timeout. This again is a very important factor. Like whenever there is no command velocity, so command velocity gets timed out after every 0.5 seconds. For example, if you are moving your bot with your joystick and suddenly your joystick battery goes off, then the last velocity the bot will remember, it will keep on moving on that velocity. It will not stop. So we use a timeout so that every 5 seconds, 0.5 seconds, it checks for new velocities. If it's not there, it will stop the bot. So it's a timeout. Okay, then enable ODOM and all those things. These are for later section. ODOM is basically the position where your bot starts in the map frame. And publish wheel data, limited velocity. Here you are defining what max velocities you want. These are in meter per second. Okay, this is rate. This is jerk. Jerk is the rate of change of acceleration. And again, this is the linear velocity. That is the forward velocity in which your bot will move. And this is the angular velocity, like the angular velocity at which your bot will move. So I have given it as 2.5 radians per second. So what 2.5 radian means? That your entire chassis will move at a maximum speed of, will rotate at a maximum speed of 2.5 radians per second. And what ROS2 control does is, when you publish the velocity that I want to move my bot at 2.5 radians per second, ROS2 control converts the overall bot speed into wheel velocities, because at the end of the day, motors understand only PWM and voltage. Now, how to convert meter per second to voltage value? So that's the entire work of ROS2 control. ROS2 control takes the input speed velocity. Like I want to move my bot at 1 meter per second. This is what humans understand. Humans don't understand PWM from 0 to 255. I'll say that move at 1 meter per second. Now ROS2 control, what it will do, it will take into consideration the wheel separation, the wheel size, the wheel radius, and all those things. And there is a formula you can use to convert the overall bot velocity to wheel velocities. Then it will publish that wheel velocities to your microcontroller. Then at the side of your microcontroller sees, okay, the bot wheels need to move at 5 radians per second. Now the microcontroller, you write the firmware code which converts 5 radians per second into PWM values. You convert 5 radian and map it to PWM. Then you'll get an output from 0 to 255, which is fed to the motor driver, and the motor driver indeed rotates the motor. The motor rotates at a certain RPM. The encoders measure it. Okay, the motor is rotating at this RPM. Again, the motor encoders reverse calculate the what this thing at what speed the what wheels are rotating. It sends back over serial to your ROS2 control. ROS2 control again reverses the entire thing. Okay, the wheels are moving at this speed. Then what will be the overall speed of the robot? Okay, so the robot is moving at this speed. So this forms a closed loop system. And in this, to fine tune it, you use something known as PID tuning to what is the set point or the desired velocity you want to reach, what is the current velocity, and how to reach that. It was out of scope of today's workshop, but it's better that if you know. Okay, so this was the bot controller thing. Now we will quickly add the launch file. So controller.launch.py, which will launch the controllers. So we are launching 2 controllers, joint state broadcaster and wheel controller. And again, since we have created a new package, we'll have to set up the CMake lists. So again, I'll just copy paste all the dependencies which are required and the new folders which you have created, launch and config, and package.xml. Again, you'll have to all the runtime dependencies it requires. I have pasted it. Now the bot controller package is ready. Now we can build it. Let me see if there are no unsaved files in the system, because then it will give us issue. There are no unsaved files. Okay. Okay. Now we will build it once again. So our workspace has been built. We will source it. We will source it. Now we will run the Gazebo thing. ROS2 launch, bot description, Gazebo. So Gazebo is running. Now in another terminal, we will launch the controllers for the bot to move. So we'll go to bot workspace and again we will source it. Every time I'm sourcing it, instead of sourcing it here, you can copy paste this command and add in your bash rc file, so that every time you open a new terminal, automatically it will get sourced. But I'm showing it how to do manually. So from ROS2 launch, from bot controllers package, I want to launch the controller launch file. Enter. So our controllers have been launched successfully. Loaded joint state, wheel controller configured. Now what I'll do is I'll try to move the bot. So to move the bot, I'll teleoperate it using my keyboard. So I'll use this teleop twist keyboard command. I'll get this thing. I'll get this. Now if I press my keyboard, the bot should move. So I'm pressing I on my keyboard. This one I'm pressing, so the bot is moving forward. When I press this on my keyboard, the bot should move back. So the bot is moving back, the bot is moving forward, the bot is turning. So yeah, our bot is okay. Let me show what's happening at the back end. So if you will see ROS2 topic list, you'll see that all these topics are running at the back end. Each node is communicating with other node via topics. So here we have this topic, wheel controller command velocity unstamped. So we are publishing to this topic and Gazebo is subscribing from this topic and moving the bot. So this command, okay, let me not use this and publish to this topic directly. So how can we do that? We can do that by ROS2 topic pub. publish. Okay, to which topic we want to publish? We want to publish to wheel controller command well unstamped topic. And what is the interface type? We are using geometry messages twist. So you can see from geometry messages, we are using twist message, and then like what it takes these parameters. Inside the twist message, you have this linear XYZ and angular XYZ. So right now in the Z direction, I'll provide it an angular velocity of 1. If I publish enter, now you can see here that the bot is rotating. So every second or some whatever rate, it is publishing a 1 radian per second velocity in the angular Z direction, and the bot is rotating. If I change it to say in linear X, I publish say 0.2 maybe, then you'll see that bot will move forward also, and it will rotate in its position also. So this is how things work at the back end. Now, if I'll see this, what this topic is receiving, then I can do ROS2 topic echo wheel controller command well unstamp. Now I can see that from this command line, I am publishing to this topic, and this topic is receiving this value 0.2 and 1.0, and the bot is moving here. This is what is happening at the back end. Once again, if you guys want to see the RQT graph, then I can show the RQT graph as well. This is what is happening at the back end. The wheel controller is there and all these things. This is subscribing, this is publishing. Yeah. Okay. Now let us see that now this thing is working or not. The Gazebo thing. Yeah, now it is working fine. Now the Gazebo Lidar is working. Now what I'll show you is, like, I have oriented this Lidar like this, but generally how is it, how it is, I'll quickly show you this. We will go to the Gazebo thing. Here we will change the samples to 360, which is by default, and we will change the minimum angle to 0 and maximum angle to 6.28. Okay, and we will change the orientation to 0. Now you should see something else. Again, since I have not made any new files, now if I launch Gazebo, and I do Lidar, so now you can see how the Lidar is appearing. This is the general trend in AMRs. Lidars appear like this. It is getting blocked due to these wheels. So now you can see the samples is the number of rays the Lidar is publishing. So there are total 360 rays. These are, okay, one second. These are the rays. And since I changed the orientation from 1.57 to 0, the Lidar became horizontal. Now you can see that before this thing, the Lidar was vertical. It was pointing towards the table. Now the Lidar is horizontal, as you can see. And this is covering the entire range. But since we, in our use case, we want to make an edge avoiding robot instead of an obstacle avoiding robot, so we will place the Lidar vertically. So again, I'll edit this back to the original configuration 1.57. So what it will do is it will turn the Lidar by 90 degrees about x-axis. So it will become vertical. Samples, we don't want 360 samples. We only want 10 samples. So the Lidar will only publish 10 rays, 10 different distance measurements it will publish. Resolution, again, what was it? Just go back to the default settings. Okay, so this is done, 10 samples. And resolution, the range, we don't want 360, we just want in front of our bot. So again, you'll have to do this by hit and trial and visualizing like what is your requirement. There is no such thing like the values. You'll have to do hit and try. So again, if now I launch the Gazebo, now you can see the Lidar again in the vertical arrangement. So now you can see that again it is in the vertical orientation. So till here we are done. We are able to spawn our robot. We are able to see the scan values. We are able to teleoperate our robot. Now quickly we will move to the logic part as to how the robot will move on its own. So for that, I will create one more package which will be named as bot script, wherein I'll write the script for the bot. So again, we'll navigate to the SRC folder where all the packages are stored, and we will create a package ROS2 pkg create. We want to name our package as bot script, and this time we want to keep, instead of ament CMake, we want to keep it as ament Python. We want to build a Python package instead of a C++ package, and we will do dependencies as RCLPy. That I want RCLPy in it, which is ROS client library for Python. Okay, if I do enter, this thing will get created. So the bot script, I guess some other package is missing. Yeah. Okay, so we will create one more package named as bot bring up. So right now what we are doing is, in one terminal I'm launching Gazebo, in the other terminal I'm launching controller. Instead of launching these two files separately, I'll create one launch file which launches all the files and nodes in one terminal only. So for that, the general guideline is we name the final launch file package which launches everything for you. We name it as bring up package. Your robot name underscore bring up. So again, we can, instead of writing the command again, I can just copy. It will be same command, just the package name will be different. It is the same command, just the package name is different. And this is again a CMake this thing package. So bot bring up is there, bot script is there, and in the bot bring up thing, we will create a folder name as launch. So we will do mkdir. So first we will go inside the bring up package, bot bring up, general file structure as every CMake package has. In that we will do mkdir launch. What this does is will create a launch folder. We have launch folder. In the launch folder, we'll paste the launch files. So now again, we will navigate back to VS Code. And in the bring up, we created a launch folder. Here we will create a launch file name as simulated robot.launch.py. Okay. And I'll paste the launch file in it. So this is the launch file. What it is doing is that it is taking in the world name empty table. It is launching the Gazebo launch file, this one which we have in the bot description, Gazebo launch file. It is launching for us with the world name argument. It is launching the controller launch file, which is this one in the bot controllers package. It is launching it. It is launching the RViz node, the display.launch.py. It is launching that as well with RViz configuration from the bot description package. And it will launch the final script which we write, but I have commented it out because I'm launching that separately. So this is the final launch file which we have. Again, since we have created a new package, we'll have to set up the CMake and this thing. So we'll set up the CMake. Only one folder we have created, launch. So we have added that package.xml. Once again, we'll have to set up all the dependencies. So it is depending on these packages. This bring up package is depending on bot script, bot description, bot controller packages, and RViz which we created. So this is what package.xml does. Once again, everything is saved. Yeah. So it's saved. Yeah. So we will build the workspace again. Export the workspace, and instead of launching the multiple commands, launch files which you're running, we will simply launch the bring up file. ROS2 launch from which package you want to take the file. You want to take the file from the bring up package. So bot bring up, from there you want to launch the simulated robot.launch.py. If we press enter, it launches RViz also for us at one command. It launches Gazebo also for us. Also, if there are, it configures the controller also for us. So in just one command, everything is done. Now, if you once again publish, again the bot should move. So as you can see that the bot is moving now, since because I'm publishing the command velocities to it. Okay, this is done. Now finally we'll write the node for the automatic movement. So for that we'll close all this. All these things are working. We will go to the bot script. So the structure of this thing will be different. As you can see, the CMake has include src, CMake and package. This is a CMake package. The Python package is a bit different in structure. It has setup.py, package.xml, and folder same as the package name. In that you write the Python code. So what we will write is, we will write edge detection.py. Edge detection.py. Detection spelling DETEC. Detection.py. Okay. And just, yeah. So everything is working. Now we have wrote this. So while running this, what you have to do is you'll have to navigate to the Python folder. Let me close these tabs. Let me close RQT as well. Let me just reset it. Now we will navigate to the where the file is created. So it is in src. It is in bot script. Again in bot script. Press enter. ls. There is this file. Now you have to make it executable. How do you do that? You do chmod +x edge detection and this. Now these two files will become executable. Now it's coming in green. Now it is a Python executable which ROS can run. So this is a very important step which you should do, or else you'll face issues. Again, since we have created the new file, we will configure package.xml. So here we are using all these message types. So we have pasted it that, and in the setup, only one thing you have to do, console scripts, you have to give the entry point as to where your code is and where should it start. So this is the executable name, which is edge detection. This is the package name, which is bot script. This is the node name, which once again is same as the executable name, but not compulsory, but it's a general trend which people follow. This can be edge and this can be edge detection. No issues, but this is the general trend. Okay, this is set up. Now finally we will write the code in it. So this is the final code for our bot to move. Let's test the code first, then I'll explain you step by step as to what this code is exactly doing. So let's test if it's working fine or not. So I'll open one in the terminal. I'll do colcon build symlink install. Also note that symlink install only works when there are Python files. If you write .cpp file, symlink install won't work. Then every time you will have to build it. So this is one more thing. And now I'll source this thing, Workspace, and I'll launch the bring up file, simulated robot. Again, I'll source it. And now here we will run the node which we created just now. The ROS2 run. To launch a launch file, we use ROS2 launch. To run nodes, we do ROS2 run. ROS2 run, from which package we want to run the node? Bot script. So bot script, and which node, which is the executable? Executable is edge detection. If we press enter, you can see that our bot is successfully able to avoid the edges. in the RViz, the fixed frame, if we will change from base footprint, right now the fixed frame is base footprint. So the bot is not moving. Instead, the odom is moving. So we will change the fixed frame to odom. Now odom will get fixed and base footprint will move. So the bot will move. And this is the starting point, the odom frame. So now you can see that our bot is not falling from the table. Now I'll explain you the logic behind this, like as to what is happening exactly. Let me just stop the script. Once I stopped the script, the bot stopped because we had timed out the command velocity. If we don't time out, then the bot will still be moving at the last command velocity published, and it will fall from the table. So let me explain you what is happening exactly. So you remember that in this file, the description URDF Gazebo file, I had kept the samples to 10. And initially I had also shown 360 samples. So the laser scan with 360 samples was quite dense, but here it's not that dense. So here you can see only 10 rays, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You are seeing 10 rays. So the Lidar is giving you 10 distance values. So what I'm doing in the code is and the distance value is given in the form of a list. The Lidar every second or every millisecond, whatever the time is, provides you a list of distances. In that, I'm selecting a specific distance value for upper rays, and this is the down ray, this is the up ray which I have named in the code. And based on that, I have written the whole logic. Let me show you the code once, then you'll understand it better. So what is happening is, first here we are importing this thing, what do you call the interpreter path, the Python interpreter path. It is very important. Then we are importing the RCLPy library for the ROS2 Python to run. Then from sensor messages, like wheel command velocities are published via twist message. Similarly, laser scan data is published via laser scan message type, which is in the sensor messages package. Okay. So here I have created a class edge avoidance robot. Here I have named the node as edge avoidance bot. If you do ROS2 node list, you will get the node name as this. So we are creating a publisher which is publishing to this topic, which I published using command line. Wheel controller command well unstep. This I did manually using the command line. I was publishing to this topic. Now I am publishing programmatically using nodes. To this, I was publishing twist message, and I had imported this type in the command line as well, geometry message twist. Okay. And this is the QoS profile, which is not required right now. And this node is subscribing the laser scan topic from the scan topic, which I showed. So the if right now also, if you see, and one more thing, like this is the scan value. This is the laser scan data which RViz is publishing, the red lines. This is showing that the table is there. Okay. And if you don't have RViz, then how the laser scan data would look. So ROS2 topic echo scan. So enter. So this is how the laser scan data will look. See, it is publishing these values 1, 2, 3, 4, 10 values it is publishing. One value is infinity because it is out of range. I have set the maximum range as 4 meters. Whenever it is out of range, it will publish infinity. So this is infinity. And these are the minimum ranges which are getting published. So this is the laser scan value which is getting published. Okay. So I'm subscribing from the laser scan topic. Then I have created a timer which does which at every 0.1 second publishes the command velocity. So here I have created two variables, up and down, and a variable named as flag. So what is happening exactly? Let me open Gazebo side by side. What is happening exactly is, whenever the scan topic receives some value, it calls this callback function, Lidar callback. So this Lidar callback function is getting called. So this ranges list from the messages, this message, like whatever data the scan topic sends to the callback is stored in this message. And in this message, we are extracting the ranges, which I just showed you, which is a list of distances, and we are storing this in this variable ranges. Now what here we are doing is we are selecting only the valid ranges, like which ranges are valid. So I want only those ranges out of 10. There are total 10 ranges, and out of 10 I only want those ranges which are more than 0.5, which is the minimum threshold limit, and which are less than 4. Okay, if any range is greater than 4, mark that range as 4 only. So in this thing, you are seeing that this range is greater than 4. This is infinity. So what this code will do is it will, instead of giving infinity, it will cap this value as 4. So this is what this line of code is doing. Then I get the valid ranges. Now in that set of list of valid ranges, I am selecting range 6 and range 2. It's just like an array. Like if you guys know how to use array and lists, then you guys might understand what's happening. So I'm selecting the, say for example, I'm selecting the second line, like I'm selecting this line, I want this distance, and I'm selecting the sixth line, maybe this is the sixth line, so I want this distance. Okay, so in the code I'm basically doing this, and every time it is printing the values which we will see in the command line. And then this was the Lidar callback, and these are global variables up and down. Then the control loop is being called. So the control loop logic is given like this, that, and when is the control loop function being called? In the timer callback, it is calling the control loop. That is, after every 0.1 second, this control loop function is getting called. So after every 0.1 second, command velocity of 0.3 meter per second in x direction and angular velocity of 0 is getting published. So whenever there is no edge detected, you can see the bot is moving forward because only linear velocity is given, no angular velocity. Whenever bot detects an edge, that is self.down greater than 0. Right now, if you see, if in this thing, right now self.down is, say, self.line is, say, this line 0, 1, 2, this line. So this line, when it falls on the table, it is always around 0.2 meters or 0.3 meters. But when it will reach the edge, its distance will increase, because then it will measure distance with respect to the ground. So in the code, I'm saying that whenever the distance is greater than 0.5 meters, means the edge is detected. So I'm doing flag as high. Okay, so the now bot is moving. Now you can see this. Up right now the values are this, and when the edge will be detected, then you see the values. Edge detected, taking turn. Now let me show you what is happening. Here the bot was moving forward. Because no edge detected, linear velocity 0.3, bot moving forward with no angular velocity. So bot is simply moving forward without any turn. The moment edge is detected, that is this self.down. That is self.down is greater than 0.5. Now here you see. Now the bot is, initially the bot was on the table, then the down value was 0.2. When bot detected the edge, that is when this part where I'm like focusing my cursor, when this part reaches this place, then the value becomes this, because now it is measuring distance with respect to floor instead of with table. Then it becomes 0.70, which is of course greater than 0.5. So it does flag high, that edge is detected, now reversing and turning. Then moment this thing becomes false, like the upper ray now is less than 0.6, that is bot has sufficiently came back, then I set the flag to false. Once the flag is set to false, since we are using AND, it doesn't enter this loop again, so the bot keeps on moving forward. Again, the edge is detected, we do flag true, again flag is true, and this thing is also greater than this, so this is both are true, we will enter. Once this thing becomes false, since we are using AND, the final outcome will be false. We'll go to else, again set this. So this was the basic code, and every 0.1 seconds, this function is called, and this, using this self.publisher, we are publishing the command velocity. And here we are initializing the node, creating an object, spinning the node continuously, and when we press Ctrl C, the node shut down. This is the entry point. So this was the full explanation of the code, and this was the final project. We have successfully completed our work. It was nice having you guys. Let's see each other in the next meet, which we will be having.
Sure. Definitely.
Okay, then goodbye.
Goodbye. Thank you so much.
Yeah.
Can we share the